Okay. Hello. Oh, there's a live Catherine sighting. That's awesome. That's hello and hello, Sulady. It's Sulady. I'm gonna ask you in public. Wait, should I? Maybe I shouldn't ask. Oh, there goes my board. Oh my God. I cannot. And hello, Sylvie. I cannot start. And hello, Ashton. Sorry. Hello, Eugen. And I know Eugen was here 45 minutes ago. Sorry, in the middle of my other class. If I ever kick you out, I don't mean to, it's because I'm in the middle of the other class. Anyway, whatever. Hold on. Sorry. You wouldn't know this, but do you know that before I start every class, I actually like make a little promise to myself and say a little prayer asking for me to not be a freak, and it never works. Like I always end up being a freak. Sorry, but I'm really trying not to be. You wouldn't know it, but all right. So wait, so who okay, wait. So good afternoon. So I'm gonna do the so video wise, yes. Hello, Ashton. Hello, Eugen. Hello, Sue Lady. Hello, Sylvie. Hello, Ariana. Hello, Marina. Hello, Kayla.
Hello.
Hello. And then she goes, okay, and hello, Marina's dog, of course, whose name I forget. And then chat-wise, yes, good afternoon, Sue Lady. Good evening, Kayla. Good afternoon, Sylvie. Good afternoon, Ariana. Hi, Dewan. Hello, Marina. Good afternoon, Giselle. Hello, Abigail. Hello, Ashley. Okay. Quick way, well, Sue Lady, are you a lab tech? Or I shouldn't ask that in public, but oh, she's connected to audio anyway. All right. Well, she has a chance to pretend she didn't hear me. Okay. Okay. Nothing like a 2.5 hour Zoom at the end of a long day, right? Am I right? Yes, I'm wrong. Okay. We have a lot to do, and maybe we'll do some of it. What I want to do, I don't want to talk at you for, I know last week was questionable. It was like super useful in a way and super not useful in another way and blah, blah, blah. But then you had this board meeting on Monday, which I've heard about now from some of you. I've heard about it from some of you students. I mean, I've heard a perspective on what happened, and I've heard a perspective from Professor Talley. And I have my own intuitions about what generally happens at board meetings. A board meeting is meant to be a discussion, and I would like today to have a discussion about the discussion. I would like to be talking at you less than I sometimes do. I do understand, however, that board meetings can often feel like pulling teeth. I mean, the whole point of a board meeting is that the only discussion really is supposed to be generated by the students. The instructor's really not supposed to say a lot, and that can be very hard on the instructor and on the students. It can actually take a lot of self-discipline for the instructor not to save the students from awkward silence for like minutes and minutes on end. I mean, even in the best of times, that can happen. Now, I gather some of that happened on Monday, some awkward silence. I mean, that may have been painful for some of you. It may have been painful for some of you who didn't want to talk and felt like you were being forced to, and then like you didn't. It may have been painful for those of you who like felt like you had to do the talking for everybody else or whatever. It can be painful. You're good, but that's not the last time we're going to do one in this class. Excuse me. I have to say, I'm a big fan of board meetings for all of the potential they have to ultimately really succeed in helping us all, ultimately. But they don't always feel that way at first, and they don't always succeed the first time we do one, et cetera, et cetera. So what I'm here to do now, okay, is I want to hear what happened. Look, partly you had this whole big sheet that you were supposed to go through in the board meeting that was supposed to start clarifying the things that weren't clear last week. Then I overly lectured at you about the clarification matters. I mean, if nothing else, our goal for today, I think, is to get answers and correct answers and feel confident about those answers to the sheets that you were meant to be doing in the board meeting. I'm going to tell you right now, though, I would ideally really like, I mean, I will talk if I have to, and I'll just provide answers if I have to. But I would really like to hear from people today that didn't get a chance or take a chance or feel a chance to talk much during the board meeting, or for that matter, the last few Zoom sessions. Like this, there are some, I think everybody here is doing work, but I'd like to get to know more people in this room, if at all possible. And I'd like to talk less. I think that would benefit everybody. So all right. So here's what I'm going to do. Let me get out the sheet from. Yeah, I'm going to open the sheet. Give me a second. I'm going to open the sheet that you were doing the board meeting. My understanding is that you got somewhat far in it. I think you got a bunch of answers, but I don't think you finished it. You'll correct me if I'm wrong in a second, but I'm going to get out my sheet. Bear with me for 1 second. I guess I'll screen share it. Or actually, unless one of you literally has it right. If there's anybody who wants, does that make sense? No, yeah, I'll get my sheet. Just bear with me for 1 second. Oh, someone's here. Bear with me again for 1 second. Ooh. Let me just get someone's here. Okay. Pardon me. Sorry. Coming. Okay. Okay. Sorry. Okay. So here's what we're going to do. I apologize for all the delay, and I apologize for my entire personality and the lack of world peace. I am going to assume that you got a lot of answers to a certain point, and then you didn't get answers anymore. So what I'm going to do is ask. I'm going to start asking now. I'm going to ask in the private chat. We're going to bang through these. I'll ask a question in the private chat. I want you to put the answer. Especially, and I'm going to say this, especially if you feel like you've already discussed the question in the lab and everything, you're already straight on it, then all the more reason I'm encouraging anybody who doesn't talk a lot or say a lot in this class, in the private chat, just put the answer as a way of showing me, like you were there, you've got the answer now, we're good, we can move on, just as a way of showing me that you might not want to say anything new or risky or whatever, but that you have the answer and you're with me. So I'm going to ask, and then we'll see where we get to the point where we actually have to discuss things. We'll find that out, and then we'll start getting a little bit more public. But right now, right now, I'm setting up the diagram for the very first question in the board meeting. What else am I missing? Right. And I'm going to say right now, as far as I can tell, these are the facts. Ones that I just drew are the facts that were given, and they are the diagram for the very first question A. So I'm going to ask now, maybe you already did it. I'm trying to go back and forth between screens. Question B. And so please also, I'm sorry, obviously I'm tired too, but it would be really helpful if you guys would all have the board meeting sheet in front of you on your side of the Zoom to follow along with me, because I can't share that screen and share answers at the same time. I mean, I probably could, but I don't know. I can't. So I'm in phase 1 of board meeting alpha. That's my diagram. That's my answer to question A. I'm going to ask you now. Can you please put, like any and all of you, but particularly those of you that I don't hear from a lot, please put in the private chat the answer to question B. Question B is, on average, how many complete cycles, round trips, does a particle complete each second? And sorry, I know I took away. Oh, you already have. All right, great. Okay. Oh, wait, have I been on mute this whole time? Wait, oh, God, wait, I'm looking in the chat now. Wait, have I been? Oh, okay. Wait, oh, I'm the back. Okay, wait. Okay, wait, I just got something in the. Wait, so someone in the direct chat just said we're up to phase 2. You're good with phase. I appreciate that direct chat person who just said that you're up to phase 2. That's really helpful to me. And I know I'm getting off to a very slow start here. I apologize, but that's helpful that you're telling me up to phase 2. But you know what? Then, if I get one other person agreeing with that, oh, cool. All right, thank you, direct chat. So someone just gave me an answer to question B, which is what I am asking. Okay, I'm going to stop for a second because I really am trying to make this, so one person did just do what I asked, which is that they just told me an answer for part B. That's great. But somebody else just said that you're all up to phase 2. If that is the case, I don't want to drag you down or slow you down. If one other person confirms that they're okay with me skipping to phase 2, if one other person just wants to confirm, and I'm just trying not to use names just out of respect, but if one other person puts in the direct chat, yeah, we can skip, or if you put in the general, whatever, if one other person says we can skip to phase 2, I'm good with that. I do not want to waste your time. I am wasting your time. But otherwise we're going to keep proceeding and we're going to bang out the answers to phase. Okay, one other person just said they're good to move on. So I'm not trying to confuse you. I'm going to turn the page to phase 2 because at least 2 of you say that's what we're up to. Good, fine, thank you. I totally appreciate the feedback, and I hope all of you, every time you participate at all in this, I hope you're submitting those sheets for points and participation because they have it. Okay, part B. Great. Okay, awesome. You are with me. All right, I'm skipping to phase 2 because it sounds like you already did phase 1 with Professor Talley. Okay, phase 2. Okay, so I'm going to phase 2 and I'm moving my screen. There's probably is a way to, well, one day you'll tell me if there's a way to share 2 screens at once. So phase 2. Boop, boop, boop. All right. Okay. Now it's all the same. I'm not going to redraw the diagram, but now y naught equals 0.4 meters from below the spring equilibrium, but everything else is the same. So the mass is 5 kilograms. The K is 500 newtons per meter. And the T is 628 seconds per cycle. All right. Now, and someone's here. Okay, we can get rolling now. God, you know, if you're bored right now, I totally understand why. Excuse me. All right. So now, phase 2 of the sheet. We already have a diagram. Diagram C above. Same diagram. Question B. So this is, again, it says, on average, how many complete cycles or round trips does a particle complete each second? This is asking for cycles per second, right? And I do recognize direct chat person. At least one person has already put an answer in the chat, which I totally appreciate. I'm going to take the answer that the person put in the chat, but I'm also going to say, before I even write that answer down, stop me if this does or does not make sense. But if the question is asking, how many cycles does this thing make per second in English or in physics terms, what B is asking for the F. It's asking for the standard frequency, right? That's what it's asking for. And stop me if that does it, like just in terms of terminology. And one person in the chat, thank you so much, person who's said a lot in the chat already. Oh, you're so nice, person in direct chat who just said they're not bored. Thank you. Okay, I appreciate it. Okay. You're also nice. All right. So one person is saying in the chat, and to be honest, it's not 100% clear to me whether her or his answer is meant for phase 1 or phase 2, but I think I'm going to go with it because I think I like it. One person says that, oh, that was before. Oh, okay. Well, one person is saying this. One person is saying this. And by the way, I think I agree. Well, yes. Good. Okay. Let's talk about this for a second. I'll check the math in a second, but I'm very inclined to agree. Okay, things are happening in the chat. Yes. All right. First of all, I totally do agree with this answer, and I already have things to say. Surprise, surprise. So first of all, thank you all for being so participatory in the chat. Okay. First of all, this answer that I just got from the chat, but I do agree with this answer. Yes, the person in the chat put it. They meant it as an answer for phase 1. But they're also saying but it seems like people tended to think that the answers to phase 1 were the same as the answers to phase 2, or at least so far. And yes, let me be very explicit about that. Yes, that is not meant to be a trick, but it is meant to be part of the lesson. Is that, okay, phase 1, you got a bunch of answers. And I'm happy to go back and talk about how we got them, but you got a bunch of answers. Phase 2 with this apparatus, what we specifically changed, we change the initial position, the initial displacement from equilibrium. I want to give you a word for that, which I'll write down. A new word for that initial displacement, a word that we use in physics, is amplitude. And I'll write that in a moment. But we changed the amplitude of this oscillation, but that's all we changed. And it seems that somehow that did not change the period or frequency of the oscillation. That's an important point. Now, first of all, how do you know it didn't change that? Or like what, like how would you know that? Or why would I expect you to know that? Only because it says in the problem, it gives a different number for the amplitude, but it says, sorry, that everything else is the same. Like we have no other cycle data to go by except the data that it gave at the beginning of the whole sheet. But that is, and that's correct. And I'm going to assume for the moment that the way you got frequency, the way somebody in the direct chat got frequency, is they took the period and they flipped it to get frequency, something we might or might not want to review at some point today. But yes, the period of the oscillation, the number of seconds per, let's just be clear. I think I've said this to some of you in private, some of you, like, period means time. Oh, sorry. Okay, I think you already are all clear on this. I just bit of notes, just so we can all make sure to be using the same notation. Whenever I put square brackets around something, I'm talking about the units of that thing, right? So I put the square brackets around T, and then I say the units are seconds per cycle, right? Then I put square brackets around lowercase f, and I'm saying the units are cycles per second. And I know you already reviewed this with yourselves and with Professor Talley, but yes, period of time is reciprocal of frequency of oscillation. One is seconds per cycle, the other is cycles per second. But and that's the and so in the first phase, you all said, okay, there's 628 cycles for 1,000 seconds. So you just divided and got, therefore there's 0.628 cycles per second. And then you flip that and said there's 1.59 approximately cycles per second. Just to be clear, also, as someone in the direct chat said, just from here on in, as far as units are concerned, one hertz equals one cycle per second. So 1 kilohertz is 1,000 cycles per second. 1 megahertz is 1 million cycles per second, et cetera, et cetera. But now, oh, and one more piece of vocabulary. Okay, to finally start getting somewhere. From now on, Okay. First of all, just to be clear, we have an oscillator, like something that's going back and forth, back and forth. Assuming that it starts from rest, assuming that it starts by you hold it somewhere other than equilibrium and you're holding it there and then you let it go. So assuming it starts from rest, then wherever it started from ultimately becomes the maximum, wherever it was initially displaced from equilibrium becomes the maximum displacement it will ever have from equilibrium. Okay, we found this out from energy conservation last week or 2 weeks ago. So wherever it initially has zero kinetic energy will always be where it has zero kinetic energy. And that will therefore always be where it has maximum potential energy. So that will always then be its maximum displacement from equilibrium. So to sort of direct our attention toward that special place that I think we did say this last week, but that special place where something from now on is maximally stretched from equilibrium and always comes to rest and turns around, that turning point is from here on in known as amplitude, an amplitude point. Amplitude equals maximum displacement Now, here's the point, though. Okay, all that I guess is old news. Here's the new point, well, you'll tell me in a minute in the chat whether how much you discuss this with Professor Talley or not. What this problem, what phase two seems to be implying, like, okay, to cut to the chase. Sorry, all the rest of the answers to phase two are going to be the same as phase one. Okay, not phase three, but yes, phase two. In fact, I'll write them right now. All of the answers. Well, you'll tell me the answers, but all of the answers to phase two are going to be the same as the answers to phase one. The reason for that is the kind of oscillation that we're talking about here, the kind of oscillation that we're talking about, the kind of back and forth cyclical motion is not just cyclical, but it's cyclical in a really, really constant, predictable, regular way. Remember, we're talking about an oscillation here that conserves energy. This oscillation will go back and forth at a rate of frequency and a rate of period that is so constant that it's constant independent of amplitude. Now this is like new information here, or this is like at least a new understanding. This kind of oscillation that we're looking at here, this energy conserving steady oscillation, this is called harmonic oscillation. And harmonic oscillation is a very special type of oscillation. Like anything can just go back and forth, and a fan can oscillate. A washing machine can undergo cycles, and anything that undergoes cycles of some kind we call oscillation. But if the cycles are steady in a very certain specific way, then we call it harmonic oscillation. And this is what we mean by that. I want to show you. All right. So I'm doing it already. I'm starting to talk more than I mean to. Excuse me. I'm going to say right now, I am going to turn it back to you guys in a minute. I really am. Let me just, I'm scrolling. Let me just look. Yeah. I'm going to turn it back to you guys in a minute. But let me cut to one chase first right now and say, oh, you agreed. I'm just looking in the chat. I'll say right now to save a moment or two. Every single one of these answers to phase 2 is the same as every one of the answers to phase 1. They are. If you're already if you're comfortable and confident with the answers to phase 1, then repeat them for phase 2. And let me show you why. This is a big deal. If you look at the math for what we're trying to establish in all this, what you discovered in the lab 2 weeks ago, you're saying that this harmonic oscillation looks something like this. Something like this. Now we're going to modify this further, but something like this is what you got in the lab 2 weeks ago. And furthermore, you said something like that, right? Now, a lot of the details of this, we still have to review and re-explain and clarify for some of us. I mean, some of this is still fuzzy to some of us, but I want to make one point that I don't think will be fuzzy to you right now. This right here is the amplitude, right? This right here, well, actually, maybe I'll ask you because I am talking too much. The why not term is the amplitude, right? Why not is the initial displacement, the number of meters from equilibrium that the thing was at when t equals 0, right? That's what why not stands for. And now we're saying that initial displacement is the most displacement that we ever see. So the why not term there is the amplitude. You tell me, please, like one of you in the chat, just to save us all from torture, that lowercase a term, which we will give a different name, or we sometimes give a different name, but that lowercase a term in there, 2 pi over capital T, 2 pi over the period. What's the name for that? What do we call that? Awesome. That was fast too. I didn't even know he was here. When did he, wait, have you been here the whole time? Okay. Yes. Awesome. Oh, sorry. I shouldn't say that. We're in a direct chat. Sorry. I mean, my son wasn't here the whole time. No, I didn't hear the Pokemon being played. Okay. Yes. What someone in the chat just said was that this term here is the angular frequency. This term here is the angular frequency. Now, the angular frequency, again, oh, you have, okay, I'm sorry. I don't know what, I'm losing my mind. Oh, that's funny. Oh, I want to know what you're, okay, that's awesome. It's all about Pokemon in the end, folks. A is the angular frequency. Again, I feel like if I'm not careful, I could talk about and review and try to unpack angular frequency to all of you for hours and hours. But at the risk of, but I'm not going to do that at the moment. Let me just remind you, angular frequency is a way of measuring frequency only in terms of angles rather than cycles, right? Like frequency is number of cycles per second measured in hertz. Angular frequency is just a way of making that more mathematical. The whole deal with angular frequency is we just continually remember, an angle is a portion of a circle. A full circle is known as 2 pi radians because the circumference of a circle is 2 pi r, right? So to go around a full circle is 2 pi radians. So 2 pi radians is just a fancy mathematical way of saying a cycle. So angular frequency, the measurement of radians per second, is just a fancy way of saying how many cycles per second, only with a conversion factor of 2 pi, right? So where am I going with this? Where I'm going with this is here. I'm saying that lowercase a term in the equation and that y naught in the equation, they're both in the equation. Oh, sure, they're both in the equation, but they are totally independent of each other. They're independent, meaning one is not an equation based on the other. One of them is not on the left side being isolated and one of them is not an output based on the other as an input. Let me be more specific now. Ooh, I'm going to take a risk here. I'm going to go out on a limb. I'm going to say, if you were to do this kind of graph, that kind of function on Desmos, if you were to make that graph on Desmos, you would notice, or you would to design that graph by having y naught be a slider and lowercase a would be a slider. Now, again, like you still might not like that. Not all of you might like doing that, blah, 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 blah. But just that one time that you were all with me in the Zoom, just watching me manipulate one slider in Desmos, all you have to have done is seen that once, and you'll realize like the whole point of sliders is that they can be manipulated. Each slider has its own name. Each slider is its own knob. A user, a researcher can play with one or play with the other or play with both, right? They're just literally like they're sliders. They're like, if you were a sound guy or a DJ in a studio, they're just two different levers that are doing two different things to the sound. They're not attached to each other. They're literally not attached to each other. This is a huge point. Honestly, you could tell because I'm screaming, right? Like, no, this is a huge point that frequency doesn't have anything to do with amplitude. It's two different, unassociated features of an oscillation. As long as you're with me mathematically, like I'm just saying right now, mathematically, one term can be manipulated and it doesn't have anything to do with the other term, which is why mathematically we can give you phase one and give you this whole like setup with a mass on a spring, blah, 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 and say, okay, we measured it. It did 628 seconds, 628 cycles in 1,000 seconds. Okay, blah, blah, blah. And then we say, okay, now we're going to start all over again. We're going to start all over again, but this time we're going to hold the mass down all the way to here instead of to there. And we're going to give you measurements again. Oh, again, it's 628 cycles in 1,000 seconds. Like mathematically, there's no problem in the fact that we went from phase one to phase two and said only one of the numbers changed and we didn't change any of the other numbers. That's mathematically, but who cares? Physically, but I'm just saying that's why it was legal. Okay, that's why like we weren't tricking you or something. But now physically, I am going to talk a little bit more because now I physically want to say like why it was worth like sitting there with phase one and phase two. So number one, right? It says look at the math. That says look at the math. It doesn't say look at my ransom note and dump like 400 unmarked bills in a suitcase under the bridge. It says look at the math. Okay, but now two. Let's look at the physical implications of this. Okay, now I'm going to beg your indulgence again. I will shut up soon as my pledge to as my pledge to you for actually listening to me. I will shut up again. I really will. But this point, I just cannot resist making. I mean, it's like kind of like a big nugget in the course is that if you're following the math at all, sort of, or just like seeing what I'm saying about the numbers, now step back and look at what we're saying physically. What I'm saying And by the way, again, the reason I would even look at the math first is not just to say I'm not lying, but I'm also looking at the math to say whatever we're saying about this example, if it's can be expressed in a general mathematical function, right, with letters rather than numbers, that means it's not special to this example. It's just the nature of oscillation in general, right? That's like why we're doing the math, so that we know the nature, the character of oscillation in general. Well, evidently, what we're saying about oscillation in general is that if I have a spring, okay, I'll just picture it horizontally just because it's easier to, well, it doesn't matter, whatever. I have a vertical spring. We're saying pull the mass all like way down to, pull the mass down to a couple of centimeters and let it go. And it goes wah, 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 back and forth, wah, wah, wah. And let's just say like it takes 2 seconds for every wah, like tick tock, 2 seconds, 2 seconds, 2 seconds, right? But then we're saying, okay, now try it again. And leave everything else the same, but pull the mass down like a lot farther. Pull the mass down a lot farther. Ask it to make cycles that are significantly, measurably larger than the old ones. Ask it to go like this now. Wah, 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 wah. What we're evidently saying is that even though we were doing wah, 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 and now we're doing wah, 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 we're apparently claiming that these wah, 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 wahs are going to take the exact same time as these wah, 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 wah. Like we're literally saying, and I'm totally going to look in the chat in 1 sec. I'll just finish the sentence, but good. I'm glad something's happening in the chat. I mean, we are literally saying you can ask each oscillation to be a lot bigger in space, but yet somehow still each oscillation, each cycle will endure the same period in time. We're saying, I don't care how big you make the oscillations, they're gonna tick tock at the same constant rate. Like it, I mean, that I have a lot more to say, but that's a little surprising. I mean, it should be a little surprising. We're saying it doesn't matter how big the oscillation is, it's still going to take the same amount of time. It doesn't matter if you do a 100-yard dash or a 1,000-yard dash, you're going to do it in the same amount of time. That's what we're saying. We're saying the spring automatically is going to adjust them as though it had a goal, as though it was like designed to produce a certain tick-tock rate. That is what we're saying. Now, wait, there's at least one thing in the chat. Let me just look. Whoa, you know about that? Okay. Whoa. All right, that is very cool. So something in the chat is very cool. And there's only one thing in the chat. So if you're the person in the chat, yes, I'm talking about you. Okay. I'm not going to read this out loud because it's like heavy. I mean, I'm not trying to, yes, it is like that. And not uncoincidentally. So basically someone in the chat is talking about light. Okay. Light, like the electromagnetic spectrum of light. Now, honestly, that's where this whole ship is heading. I mean, I'm not blowing it off, or I don't want to dismiss it. Like, that's ultimately what we're trying to build in this whole course. We're trying to land on exactly what are the fundamental ingredients, or what's like the nature of what the heck is really going on with light. Because light is, I think, very exciting. And I mean, light is the ultimate intangible, right? I mean, we all know what it is, but none of us really know what it is. And it's always there, and it's the way we see everything, but we can never see it as such, light, I mean, right? I mean, it's ever present, but it's like super hard to put your finger on, literally and figuratively. Now, ultimately, this whole course, we're trying to build from things that are concrete through things that are increasingly abstract, all the way to the ultimate abstraction, which is light. So someone in the chat is saying something about light, and they're not crazy to be bringing that up. I will say, so yes, this is like that, or maybe the other way around. Maybe light is like this. Ultimately, light is what light is a whole collection of highly patterned, highly organized, highly intricate, and highly abstract harmonic oscillations. the fundamental ingredient to light is harmonic oscillation. The fundamental ingredient to all abstract immaterial phenomena is harmonic oscillation. That's why we're spending so much time on it. So it's a great question. Now, I don't know if I can connect all the dots between this and light right now at this moment. But yeah, that's definitely on track. Let me say to everybody, though, what we're really talking about here is what I'm really trying to say is that a harmonic oscillator is something that keeps time irrespective of space. Like, that's actually very deep. A harmonic oscillator is something that's separating out the issue of time from its connection to space. Like, what any clock is something that goes back and forth, tick tock, tick tock, tick tock, right? But any clock you ever observe or any clock you ever use is something that's moving back and forth in time and space, right? Even a clock, if you look at it visually, it's always using space at some level to indicate time, or we're always using an interval of space to cut through and flow in time. But so at some level, it's like very hard to separate time from space. Like, to measure time, you need something that's moving through space. But what I'm saying that I had never thought about until I thought about it, what I'm saying is that a true clock measures time in a way that is not affected by space. So what I'm saying is, like, I'm saying that there's something about a mass on a spring, or a bob at the end of a pendulum string, or something known as a resistor, capacitor, electronic circuit, like it, or an atomic oscillator, or the electric magnetic field magnitudes in what is ultimately known as light. I'm saying that anything that oscillates harmonically goes back and forth at a certain tick-tock rate, a certain period, a certain frequency, goes back and forth at a certain rate that actually doesn't get affected even if you ask the back and forths to be much larger or much smaller. Now, that's actually weird if you think about it. Like, we're literally saying if you start the mass all the way down here and ask it to undergo 10 centimeters of amplitude, it will do it in exactly the same amount of time as if you ask the mass to undergo 2 centimeters of amplitude. Now, I am going to pause here and turn it back to you for, sorry. That wasn't about you. I'm going to turn it back to you and ask you, how could that, let's break this down for a second to make sure you understand what I'm saying. I mean, there's a lot of history to this, and there's a lot of industry to this, and then there's a lot of math to this. How could it be if I'm saying that the mass, when it was doing an amplitude of 20 centimeters, so each time the mass did a trip of 20 centimeters, it somehow did it in the same amount of time as when the mass did a trip of 40 centimeters. I'm gonna pause and ask you in the direct chat, tell me how it could be. How could an object get displaced 20 meters in the same amount of time as an object that gets displaced 40 meters. Like, what has to be true about the object when it's going 40 centimeters? If it's taking the same amount of time as the object that's displacing 20 centimeters, like what must the object have adjusted in order to do that? Do you see what I'm saying? Like how there's got to be something that got changed. If the time is constant for two different distances, which is what I'm arguing. I'm arguing I don't care if the mass is going back and forth between these 2 points or the mass is going back between these 2 points. Either way, it's the same amount of time. I'm asking you guys in the direct chat, how can an object do two different distances in the same time? What aspect of the object must be changed if two different distances are done in the same time? Do you see what I'm at? And if you don't understand, put something in the chat. If you literally don't understand what I'm asking, put that on the right track. Okay, there's one person in the chat, but now there's two people in the chat. I'm gonna wait. Okay. Now there's three people in the chat. One person's in me. I'm gonna wait for there to be one more thing in the chat, and then I'm gonna back up. Like at least one person saying they're not quite sure they know what I'm asking, which is fine. So I want to wait for one more, especially if you've never participated yet. Put something in the chat, even if it's to admit you need me to back up. Oh, wait. Okay, on the right track. That's good. All right. So people are paying attention. I appreciate it. But no, it does sound like I need to back up for a second. And really, and like clear your minds for a second. Because I'm trying to say something that's like deep and powerful, but what makes it deep and powerful is that it's like simpler than you might think. It's not, I'm using math to make an observation. Observation is like a very real world, like intuitive observation. In fact, I will say that out of five things in the chat, I want more people to be in the chat. I'm going to respond directly to each direct chat right now. It'll take me 2 seconds, but I think it's worth it. If you haven't responded to the chat, say something. Even say, sorry, I admit I'm not paying attention or whatever. Or just say something so I know where you are. But hold on. Okay. Ah. Okay. 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 I think I just responded to everybody. Okay, okay. I think okay, okay. And I will again, I'm watching the clock. I'm gonna keep my promise. I'm not gonna talk about this whole time, but I'm gonna make this point clear. All right, let me back up. So some of you are with well, those of you who are in the chat, again, thank you. Like you're with me, but I mean there's no but, you're with me. Let me explain what I'm going at here. I'm all right, all right. Shift gears for a second. I'm going to tell you a little story, okay? Like clear your minds for a second. Clear your minds from the math and from the lab and all that. Just transport yourselves to approximately the year 1620. You're in Italy. You're in the Sistine Chapel, okay? Which is like this gorgeous big building. It's like church, okay? You're in church. You're sitting there and you're watching the chandeliers, the big light fixtures, like up at the in the roof of the Sistine Chapel, and they're swaying back and forth. They are like big pendulums, okay? And you are with your friend Galileo, who's very observant, and who, despite what you might have learned in third grade, is definitely a devout churchgoer who is serious about going to church, stuff like that, but whose mind occasionally wanders in church, like many people's occasionally, no matter how devout and pious and non-rebellious they may or may not be. But you're with him in church, and you're watching the chandeliers go back and forth in the wind like pendulums, okay? And then you idly notice while you're watching the chandeliers swing back and forth, you notice the same thing that Galileo notices. And this is now in reality, right? I mean, this is in the real world. I mean, it's a historical world, but it's not like in a lab. It's not controlled conditions. And it's not math. It's not like idealized, like Op Smurf Village equations. You're just looking at a big, long, heavy pendulum that's going back and forth and back and forth. And because it's a realistic pendulum in the real actual world, with like wind and maybe a bit of friction and stuff like that, the pendulum starts to damp down in its swings. Like realistically, the swings start getting shorter and shorter in time. You with me so far? Like the way realistic pendulums do, or like the way your realistic mass on your springs in the lab, like they didn't actually go on forever like a homework problem would. The oscillation started getting shorter and shorter in space, right? So you watch these chandeliers going back and forth in the Sistine Chapel, and they're swinging back and forth. But those they started swinging in the first place because of wind, and then the wind is dying down or whatever. And so the swings start damping down. The swings start getting shorter and shorter in space, in arc length, i.e., the amplitudes of these swings, these realistic pendulum oscillations, start getting smaller and smaller. Okay, no surprise there. Like, again, totally realistic, just dramatic, because they're really huge pendulums that are really long and really massive at the bottom. So they behave like fairly like vividly, and they last longer than little dumb masses in a lab do, right? So they're like extreme pendulums. They're very vivid pendulums, but they're still realistic pendulums. So they start damping down in amplitude. I'm going to pause right now. I haven't said the punchline yet, but just please give me an electronic hand if you're with me so far. Like, can you picture the situation? This obviously is a real situation. Can you, if you just, even if you don't know where I'm going, are you with me so far? That's 2, that's 3. I appreciate it. I totally appreciate it. That's 4, that's 5. Okay, and that's asking who has. Okay, yes. Oh, and a yes in the chat. Cool. Okay, so thank you. That's good enough for me. Good enough for government work. So you're watching this thing, right? Or you're Galileo watching this thing. And you're like, fine, that's no big. I mean, the amplitude is getting, and whether or not you use the word amplitude, you notice that the length of each cycle in space is getting shorter and shorter. But as you're watching this, you're like, wait a second. Even though the length of each cycle in space is getting smaller, something gives you the sense that the time for each cycle is not getting shorter or longer. You notice that the pendulums seem to be keeping a steady rhythm, even though their cycles are getting shorter in space. Their cycle durations do not seem to be getting shorter or longer in time. So you first of all have to conclude, if that's true. Wait, I'm just looking at the chat. I think the chat is just, yeah. Okay. So first of all, that is surprising. Like, I don't know what to say first. Yeah, that is a little, I mean, maybe you don't think that's surprising. I think that's surprising. I think Galileo thought it was surprising because you figure if the things are getting shorter and shorter, like if I have a shorter distance to go, if I'm a traveler, if I'm a car, if I was driving 100 miles and it took me an hour, if then the next day I drive 50 miles, you'd think that would take me a half hour. I mean, all other things being equal, but evidently all other things are not equal. Today, I drive 100 miles and it takes me an hour. The next day, I drive 50 miles. The next swing, I go 50 centimeters. And again, it takes me, let's say, a minute. Like, so it's like 100 centimeters, a minute. But then 50 centimeters, it again takes me a minute. So part of what I was asking 2 minutes ago to everybody in the chat is, what must be happening just in yes, physics terms, but in simple physics terms, if each length is getting shorter, but the times are not getting shorter. If I did 100 miles in an hour, but then I did 50 miles in an hour, and then I did 25 miles in an hour, what must be true of the car, or what must be true of the object? If each shorter and shorter distance is nonetheless taking the same amount of time, what must the object be doing? Someone put in the chat, like, and 2 of you already did put this in the chat, like 2 of you are already with me, but I'm just repeating the question that I asked a minute ago. If distances are getting shorter, but times are remaining the same, then in simple physics terms, like no other, like I'm not talking frequency, I'm not talking, just in regular physics 101 term, close, really close, even less fancy than that, direct chat person, and there's only one of you right now. It's that type of term I'm looking for, but even less fancy, a term that you, yes, okay. What at least 3 of you in total have said, what I'm looking for is, in simplest terms, speed, velocity. Like, if this is a big deal though. This really is a big deal. I'm saying that this realistic oscillator known as a pendulum, as it's slowing down, like, oh, that thing is slowing down. Evidently, it literally is slowing down. It literally is slowing down. Like, as it runs out of as the spaces get smaller and smaller, evidently, it actually goes slower and slower. And evidently goes just slow enough to always maintain a same amount of time. Like you look at the pendulum and maybe, like, it can keep time, like this pendulum that's swinging back and forth, evidently can keep time even while it's running down. Like, please think about this for a second. I'm saying Galileo noticed this and he was like, oh, wait a second. Maybe we can make a mechanical clock out of this. Like, this is the beginnings of the mechanical clock, as opposed to the sundial, or as opposed to the super, super primitive, super unreliable, like hourglass, like, you know, dripping bits of sand from one thing to another. Like, the clocks that we had until this moment were either huge cosmic weird, like from outer space, like shadow things that were super imprecise, or they were like little jars with sand dripping down that were like nice to a point, but basically if you took them on a boat, they wouldn't work at all. And that was a huge problem, because if you can't keep time on a boat, you don't know where you are. And I'm happy to do a whole sidebar on that if anybody wants. But I mean, it's very hard to navigate at seas if you don't know what time it is. Like literally, this is a huge historical problem. It accounts for tons of shipwrecks, and also accidental discoveries of continents such as ours, or discoveries by like white Europeans. But so what I'm saying is, Galileo looked up and he was like, wait a second, that thing is keeping time even while it seems to be slowing down. Because while it's slowing down, it's literally slowing down. So it's not slowing down. And if that sounds like a paradox, like, yes, we're saying that a harmonic oscillator, when you release it from here, it has a certain amount of potential energy. So then as it's moving in toward equilibrium, it converts its potential energy into kinetic energy. If you start it from way back here, it starts with a lot of potential energy and therefore ends up on average with a lot of kinetic energy. But if you release a harmonic oscillator from a smaller distance, you give it less potential energy. So it converts to less kinetic energy. So oscillators that have smaller distances to go actually, on average, travel slower by exactly the right amount to make the time work out the same. So we build clocks from harmonic oscillators, like anything that is a clock, whether it's super modern, digital, electronic, whatever, or classic mechanical, like pendulum grandfather clock, or spring-loaded Swiss, like wristwatch clock. Like anything that is a clock is first and foremost fundamentally a harmonic oscillator, because an oscillator is something that keeps time even when it doesn't keep space. And what that really means, that I'm yelling about, is I'm saying nothing is perfect. Nothing is perfect in the real world. But I'm saying oscillators are good enough at keeping time that even if you don't know any of this that Galileo later did to later prove his conjecture, even if you don't know this math or have it in your mind, you can look up at a chandelier and notice visually that it's freaking keeping time, even as it appears to be slowing down realistically, even as the clock seems to be damping out and running down as a clock. It's actually not running down. It's slowing down appropriately so that it continues to maintain a constant frequency and period independent of its amplitude. Galileo saw this visually and then went home and not only showed why it was true, but then went home and discovered all of the things that you learned in Physics 203, Physics 101 about inclined planes and gravitational acceleration and velocity and acceleration and ramps, all this crap. Some of my best friends are physicists. No, all this kinematics that you learned in Physics 101 is all based on experiments that are done on inclined planes with objects that are moving through space and time. Here's the crazy part. how those experiments were done and how those data were collected and how those conclusions were arrived at were done by a guy who first had to know about physics enough to build a clock from physics in order to make the time measurements to do that lab. Like those labs. Like there weren't stopwatches, there weren't clocks at all. There was a guy who looked at a phenomenon and was like, whoa, that thing is so steady in time that not only does that provide me with an exciting conclusion, but in fact, now I have a tool to, in fact, start doing physics. Like that's how fundamental a harmonic oscillator is. It is our ability to measure time, because a harmonic oscillator by definition has a frequency and therefore period that is independent of amplitude. A harmonic oscillator keeps time even while it doesn't keep space. Does that make any sense at all? We're just going to stop for a second. Does that make any sense? She's like, yes, I roll. You just raise your hand if it makes sense. I'll move on. I'll shut up. I'll turn it back to you. But like, that's the wait, someone just give me something. Just thumbs up if it makes sense, if you get what I'm saying. Okay, that's good enough. Thank you, Kayla. Thank you, Salady. Thank you, Eugene. Then Eugene walks away. Ashton like smirks. Okay, Abigail, thank you. All right. So that's why all the answers to phase 2 don't change. Okay. Okay. I'm gonna move on now. I've had my fun. Let's move on to phase 3. I'm going to turn it back to you guys. Or if you have any questions or concerns about that, put it in the chat. But by the way, that's now a takeaway for this course too. I'm saying from now on, and there's more math that we have to do and more other stuff, but the definition of a harmonic oscillator, like oscillator just means to cycle back and forth. But if you're oscillating harmonically, it means you're oscillating with a frequency that is so constant that it is independent of your amplitude. That's what harmonic oscillation means. It means it doesn't matter how big the space is, the time is still the same. I can't emphasize that enough. So a harmonic oscillator is a clock. Fine, let's go to phase 3. Clearly, I need to take a breath and get a life. Phase 3. Okay, and I'm going to switch back to sheet. Now, I'm going to say right now, well, I'll draw. But I'm turning it back to you. So I'll start drawing the diagram again if it's anything different or anything like that. But please start, give me answers in the chat if you have them, or if this is where you need answers from me, tell me. But we're up to phase 3. Phase 3, same diagram, just different mass. Okay, so I'm going to draw a diagram, but I'm going to ask you question B in phase 3 is same deal. How many cycles, round trips, does a particle complete its track? And I'm going to say this time the answer is different. It's not the same as the answer from before. So we're going to you're going to do it or I'm going to do it. But here we go. Oh, wait, no, sorry. Yes, that's all the way. Okay, so B is asking, okay, so here are the new facts of the problem. And I'll remind you one other thing. I'm turning it to you now. I really am. I mean, I'm warning, come back from the fold. I'm turning it to you. Just remember, previous mass was 5 kilograms. Okay. So question B, what's the period? It's up to you now. I'm looking in the chat. Oh, good. There's things in the chat. Okay. Okay. Oh, by the way. Oh, okay. I see 2 things in the chat. Good. So, and I've turned the light. You didn't get to phase 3. I think that's what you all told me. I do understand. I think all of you did not get to phase 3. That's fine. So now we're doing something that's worth your time and money now. but I'm still going to have you guys do it. I'm not going to give the answer yet. You totally can do this. So I'm going to ask you to think about it right now, like individually. Think about it. Try to come up with an answer. So one person in the chat has just told me you didn't do it already. Right. I understand that. Another person in the chat is telling me that changing the weight, the mass. So we're changing the mass now, right? That's the one change I'm making, is changing the mass. And one person in the chat is saying, well, that's going to change. That's going to change the kinetic energy and therefore the velocity, and thus will change the frequency. I agree. I do agree with that person. Like, now that I've changed the mass, I do think it's going to have an impact on the frequency and or the period. I do agree. Now but I'm not going to let us off the hook. So I do agree. But I think we can push it further. I think you could actually get an answer. I'm going to give you hints. Like, you literally can get an answer question. I will remind you that your answer for period in the above cases was 0.268 seconds. Now I'm going to give you two hints here. Number one, I think thinking in terms of period in this case is the most straightforward, helpful thing to do. Like, rather than thinking in terms of frequency or angular frequency, I think thinking in terms of period is the most straightforward thing to do. I think even without the whole yelling and screaming that I just did for the last 15 minutes, I think all of you in the room do know what will happen to period if we change the mass. I think you know mathematically. I put another way, I think you know a relationship between period and mass for a harmonic oscillator. And I think you know it even if you did not get up to phase 3 of this board meeting. I know you do. I could give another. I guess one last hint is I think you all know the relationship between period and mass from work you did even before this board meeting, perhaps even before the most recent lab, perhaps even before the lab before that. I think if you go back in your memories or in your notes to earlier labs, you'll realize that somewhere in this course we began, I shouldn't have said began, but somewhere in this course, you experimentally derived a relationship between period and mass, and you did so correctly, confidently, like it was back before anybody was confused about anything, if that means anything. So I'm going to pause. I'm not trying to torture anybody, but I'm basically encouraging you to go back in your notes or look back at old labs. What we want here is some relationship between the mass of an oscillator and the period of an oscillator. And you know it. And I'm going to wait. Actually, I'm going to run to use the facility, and I'm going to turn off my video. I'm going to mute, and I'll be back in 5 minutes, and there'll be tons of stuff in the chat when I return. Well, actually, do me this one favor, though. Even if you don't know the answer, and of course, I'm not trying to put anybody on the spot. I'm just trying to keep our blood flowing and keep our education high. So just do me one favor, though. If you understand what I'm asking, even if you don't know what to do, but if you know what I'm asking, can you please give me an electronic thumbs up? That's okay. That's awesome. The dog gave me a thumbs up. Okay, Ashley, thank you, Giselle, Catherine, thank you. I like the clapping. That's so encouraging. Thank you, Salady. Thank you, Abigail. Thank you, Giselle, Catherine, Marina's dog. Eugene is sort of looking at me like I'm a crazy person, but that is because I sort of am. No, she's not. I'm sorry. Okay. All right. So that's a question. And you can also, by the way, I'm literally going to leave for a second. I'm going to do an oil change for a second. So I'm going to turn on mute and turn off my video. You're welcome to talk amongst yourselves. Like, you can help each other. Consider it a board meeting. But I'm looking for a relationship Aren't we all? Well, why don't you just go on JDate? No. I'm looking for a relationship between mass. Thank you for laughing. Between mass and period. You definitely have one somewhere in your notes. You do. Like I've seen, like you shared it with me at one point. But okay, so I'm gonna stop the video. I'm gonna mute for a second. Oh, guys, if I say to you that I love you unconditionally, but also professionally and, in an academic way, if I say I love you unconditionally, would you infer from that I'm saying that if I did love you conditionally right now, we'd be disappointed? Guys, okay, here's another hint. I'm talking about lab 2. Look back at lab 2. I think it was lab 2. The whole point of lab 2 was that you derived a relationship between period and mass. It's that relationship that you want here. I'll just say that. But we are going to sit in this torture until, I'm not trying to torture anybody, but we all know that me lecturing is certainly torturous in its own way. Oh. Okay. Okay, wait. 2 things just happened. That's good. Wait, actually, 3 things just happened. My son also just asked me for money. No, okay. Just kidding. Hold on. Sorry. Oh my God. Literally, my son and my father just both asked me for money at the same time. That's crazy. Sorry. Sandwich generation. Wait. Okay. Okay. So 2 things just happened in the chat. One was public, which was very gutsy and awesome. Now, I will say to Marina, since you're going public, and I totally appreciate that. What we were doing, and I really appreciate it, especially because like you're saving us all from awkwardness. What we did linearize. We did get a straight line relationship, yeah, but it wasn't like we actually found out that period was not directly proportional to mass. I think you'll remember this when I say it. But as someone in the direct chat has said, what we found, actually, I'm going to wait. I will say the person in the direct chat, and there's one person, that person is correct. But before I say it, I would like one other person to weigh in, or Marina to adjust. Like Marina, we did find that period was directly proportional to something, but the something was not mass itself. It was some function of mass. I don't know if I'm making sense. And for what it's worth, again, I am agreeing with the person in direct chat and commending that person.
Yes, it makes sense. I'm going to go back to my notes to try to remember what exactly it was.
Okay. but other people really, like, you do want to get involved here. I mean, this is a bit of a, I mean, it is silly for me to get all abstract or all detailed if we can't all be together on the fundamentals here. Like, oh, wait, okay. So there's more happening in the direct chat now. Thank you. You're saving. Yes. Okay. And I'm sorry. I apologize. There's like a lot of things in the direct chat now. I missed. Maybe you're cool. Now we're wait a second now. Wait a second. Now I'm intrigued. Okay, now a lot of things are happening in direct chat, and a lot of people are correct. So you're also making me feel better here too. So keep it coming. 1 second. Hold on. Okay. Okay. Now. Okay. Okay. Now a lot of things are happening. Okay. Okay. And I appreciate it again. I know this is torturous, but all right, here. So, and hopefully I responded to everybody in the direct chat. I mean, I don't always do that, but hopefully I did, because I'm starting to get some different things in the direct chat too. So what I'm looking for here, what a bunch of people are telling me in the direct chat is, I think what you established in lab 2 is that period is proportional to the square root of mass. Like, that's what I think we found in lab 2. Like, we did find that period was directly proportional to something. Like, yeah, that was back. We were linearizing things. We were taking advantage of the straightforwardness of linear graphs, but we deliberately, remember, we tested these different functions, and the one that we actually got a straight line graph for was when we put period on this axis and we put square root of mass on this axis. That's where we got a straight line. In other words, I think we found, and definitely tell me the direct chat if this, I mean, if you put something different, or if this is confusing you or contradicting you, like, definitely tell me. But I think what we learned in lab 2 is that period is directly proportional, not to mass, but to the square root of mass. That, okay, fair enough. Okay. Okay. Now I want to be, now in fact, let me be clear on the board here. Like, because this is where we get what we said is this. Now, this is we didn't, and I want to be clear, and this is really the way physics actually, or science, like, really often proceeds experimentally. We did not derive an equation. We, as yet, from that lab, we don't have an exact equation yet. We derived a relation, a proportionality. We found that as the square root of mass goes up, period goes up. Or more specifically, we found that if you double the square root of mass, if you, like, double the square root of mass, then you double the period. But we didn't find like a thing that you could plug into. We didn't find a full equation yet. Wait, is that true? Wait. Oh, okay. I'm looking at the chat again. Okay, good. I hope. Okay, thank you. Okay, cool. So I'm saying this. In physics, in math, that symbol, proportionality, direct proportionality, yes, it means that symbol, direct proportionality, does not mean equal to. If I say, period is directly proportional to the square root of mass, what it means is that period is equal to some constant number times the square root of mass. I don't know what that constant is if I say direct proportionality. In other words, there's no plug-in possibility. If you just tell me the mass, I can't figure out the period. But if you tell me how the mass changes, then I can tell you how the period changes. So this is another one of these. This is a very important math distinction. Direct proportionality means if you tell me how the independent variable changes, I can tell you how the dependent variable changes. There's nothing to plug in here. But there's a rate of change. So back to the questions that we're trying to answer. Here, phase 3. I think it's phase 3, question B. I'll tell you the facts, and then I'm going to leave it to you again. It's question B. Like one person in the chat did give me an answer already. I'm not. Well, I was just going to say, wow, how honest. Okay. Someone in direct chat just receded their former comment. Well done. Yes. Good talk, because yeah, I'm not sure it was correct either. Okay. All right. So you're going to see now. So I'm going to leave it to you. This is what I'm going to tell you guys. Right. And I want to make clear, we don't have an equation to plug in yet. Where are we ultimately going with this? Yeah, we're ultimately trying to figure out a full equation we can plug in. Our data has not given us that yet. Here's what we know from our data. Okay. What we know. So I'm doing a part B of phase 3, where it asks, on average, how many complete cycles round trips does the particle complete each second? In other words, it's asking what the period is now. Now, I don't know what the period is now. And I'm arguing I don't have an equation I can plug in. But the thing is, I know what the period used to be. when the mass was 5 kilograms. Now the mass is 20 kilograms. The mass has quadrupled. I'm asking you in the direct chat, please, in the direct chat, what I'm asking you is, what happened to the period if the mass has been quadrupled, if the mass has gone up by a factor of 4? What do you believe? I'm sounding really intense. I'm sounding like I'm angry, but I'm not. I'm asking, if the mass has gone up by a factor of 4, what has happened to the period? According to the proportionality that we learned in lab 2, so again, you're not going to plug an equation. I'm looking for a relation. According to what we learned in according to what we learned in lab 2, people are in the chat. Ooh, that's true. I didn't even look at the answers yet, but I'm just excited that there's 2 people in the chat. In fact, I'm not even going to look at the answers until I get 2 more things in the chat. Like, I'm going to repeat the question again. The mass quadrupled. What has happened to the period according to our conclusion from lab 2? Okay, I'm looking at the chat. There's 3 things in the chat. I'm so excited. Oh my God. I'm so excited. You guys, you should really do this. We should talk like this more often. Okay. I'm looking in the chat, but keep going. I mean, if I get 4 in the chat, I should start. Oh, maybe I should start opening up a portal. Oh my God, that would be so cool. Okay, I'm thinking of a portal where like, if we get 5 people in the chat, then all those 5 people submit for points, and then they all get points but thresholds. Talk about, it'll be like multiplayer co-op, like squared. Like, I'm definitely going to do that. The more people that go in the chat, the more people can get the more points, so that you all can encourage each. That's really weird. Okay. Anyway. All right. So now I have how many people in the chat? I have 1, 2. I'm looking for 1 more person in the chat would be great. 1 more person, even if it's to admit that you don't understand the question. And by the way, please remember, you get extra points for wrong answers. Have you ever had a class like that? Remember, if you put a wrong answer in the chat, there is a extra portal just for you. I know, right? Isn't that cray? Yes, it is. So please put things in the chat. That's how desperate we are. No. Oh, that's another person in the chat. That's 4 people. Okay. All right. So now I'm going to read the stuff in the chat. Oh. Boom. Close. Good. Boom. Oh, and actually I was wrong. There's like 6 people in the chat. Oh my God. It's like a family reunion. Wait, there's a lot of people in the chat. Okay. I'm very excited. Should I respond? Yeah, all right. To cut to the chase, and again, I'm going to say, I'm not going to respond to each one. We're on a roll here. I'm not going to respond to each one directly yet. I'm just going to get to it. We're going to say some of you are correct, and some of you are less correct. But please don't take. All of you are on the right track. All of you have clearly heard the question, and any of you who's incorrect can get even more points for the guts that you showed and the vulnerability and all of that. So please don't be discouraged if you haven't been correct. And one of you also put something that at least one of you said. Well, I'll start with it. So the mass increased, right? And period is directly proportional to the square root of mass. So first of all, it is true that if the mass goes up, the period should go up. And one of you totally put that in the chat. One of you put the period increases. Totally right. I will admit that I think we can go even farther. We can get even more specific. We can even be numerical about it. We can say the period increases by how much. But let me start by saying that is a good conclusion already. Yes, if the math, and it's not obvious, it's not always the way. It could have been something else. But in this case, first of all, yes, if the mass is going up, the period must be going up. That is good. On top of that, what a number of other of you has said in the chat too is, if the mass went up by a factor of 4, the period must go up by a factor of 2. That's what some of you were saying in the chat, and you are correct. And we are friends. We're all friends. We're all friends. But yes, if the mass went up by a factor of 4, the period must go up by a factor of 2. Why? Because we're saying period is directly proportional to the square root of mass. So the square root of 4 is 2. It's that straightforward. Like, that's literally what we mean. When we say period is directly proportional to the square root of mass, we don't mean that we have a plug-in. I don't know. What if you tell me the mass, I can't tell you the period. But what it means is if you tell me that the mass doubled, I'm sorry, if you tell me that the mass quadrupled, I tell you that the period doubled. If you told me that the mass went up by a factor of 9, I would tell you the period went up by a factor of 3. The period goes up as a function of the square root of the mass. Are people with? Are we with me? So yes, the answer is the period doubles. Therefore, the answer, okay, that's the purpose of what you found out in lab 2. So here, so the answer. So previously on the last episode of Yaverbaum Busts a Gasket, so period in phase 1, let's say. Well, I'm just going to the same number of significant digits. Yes. Okay. Are we? Just raise your hand if you. I mean, whether do you under? Even if you didn't understand a minute ago, just give me an electron. Give me an electronic hands if you're with me so far. Cool. Thank you. All right. Awesome. Thank you. Good. Okay. So that's the answer to that. Okay. Great. Oh, and Remy, are you raising your hand to say that you're with me, or do you also have a question? Okay. Great. Thank you. Okay. So that's the answer to that. So we're making tracks now, but that was like the big point of, yes, you could tell because I'm yelling. Where to go? I'm going to the next one now, or trying to go to the next one now. Right. Okay, 1 second. Sorry. Okay. 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 I just lost it. Where I'm looking for the sheet. I lost the next question. Where did the sheet just? Okay. All right. So that's that. Okay. So now, now I'm going to turn it to you again because I know I'm yelling. That was the insight. Now that is an insight. That's like anything else in physics. Do I think that was obvious? Do I think it was like falling off a log? Duh. No. But I do think once you realize it, then it makes sense, right? Like it's like everything in physics. It's totally absurd until you realize it, and then once you realize it, it seems totally obvious. But it's the insight. The insight was we know that period is directly proportional to square root of mass. So that was B. But now from here on in, all the questions are based on that answer with the exact same logic as all the questions were in phase one and phase two. Like now it's the same logic as before. So actually, honestly, I think this is a perfect review moment now, opportunity. I'm going to get your permission or your tacit consent, whatever. Like I'm going to say now, no one did phase three before, but I just gave you the major insight of phase three, and you don't have to use that insight anymore. Like you use that insight to get your new period now. It's just literally double of what it was before. So now I want you to do right now in real time, please, all of you, do C and D to complete the sheet. Oh, and we are going to complete this whole thing today. Wow, I know this is a long class, but we're actually going to complete this. So let's please do C and D. I'm telling you, it's the same logic you did for phase one. It's just now the same logic based on a different answer. So please, right now, in your own, you can even talk amongst yourselves if you want. I mean, I'm here, but please now, I'm going to look at the screen. Can I just get a show of hands if you just understand that I'm asking you to right now in real time? Do you see? Thank you, Ashton. Okay, it's good enough for me. Okay, so do see. Oh, and that was Salady. Thank you, Salady. And Salady, are you a laptop? I'm going to stop asking that. Okay, great. But like Salady has a C14. I'm just saying. Okay. All right, Kayla, thank you very much. Awesome. So do C and D now, please. I will shut up. I'll give you time to do it. And I will. In fact, I'm going to get rid of my board. I'm going to do it so I have the answers ready to go for you. We're done, but I'm going to remove my board. So I'm going to stop talking now. Okay. So, oh, I'm looking in the chat. Oh, there's a lot going on in the chat. That's good. That's good. Wait, wait, okay. Oh, wow. Okay. Wow. I'm impressed, guys. Okay. Okay, wait, I'm looking back. All right. And what time? Okay. Got the same answer. Oh, wait. Oh, and I missed something. Oh, okay. Sorry. Was the answer to C? Oh, very good. Okay, wait. Actually, I'm going to respond to some of these direct chat things, and then we'll get going. Okay. Excuse me. Um, wait. Oh. Huh. Right. Sorry. Oh, great. Okay. Excuse me. I'm looking at time. I'm going to start going over this in a moment. I'm just looking. Oh, okay. Thank you. Okay. Cool. Okay. So this seems worth talking about. So people are doing things in the chat. I appreciate it. And, we're now again, it's late at night. It's a long class, but I would say that we're in and I need to make a habit of more trying to start this way, I guess, in class, because I feel like this is class now. Like we're all in different places. I can tell from the chat, but it feels like we're getting something here. Like like this does seem like the material we need, which is good. And I'm watching the clock. I would like to get to the end of the whole. So here's the deal. So I'll just all right. Hopefully I responded to all of you in the direct chat. Let me turn on my board and show you what I have. So I'm just going to talk now through my answers, but you're going to stop me if you don't understand something I say. You know, and I've been talking with some people in the, I feel like I know what some of you understand and what you don't from the office, and others of you I don't. So anyway, whatever. Let me just turn on this board. So we're up to C. Now, C, you know, in C, the period is 1.26 seconds approximately. But before I go any, but I'm going to show you how I did this now. Now, this is not the only way to do it. I know you could just crunch the numbers as they are, but oh, wait, something's in the chat. Sorry. Okay. Oh, wait. No. Oh, let me back up. Okay. Hang on. There's like at least two people are saying something very important in the chat, and they might think that I'm criticizing them. Okay. I'm going to try to say this without going on a whole. So look, we're trying to derive equations here in this class for good and for bad. Of course, I think for good, we're trying to build physics in the manner of physics. We're trying to make it so that everything we actually believe and accept, we believe and accept because we have a reason to believe and accept it. We're trying to derive everything from either experimental data or mathematical logic, like, because this is the way physics actually does proceed. We're trying as best as possible not to just accept anything on blind faith, right? In some ways, that's much more appealing once you get used to it, because we're not it also makes things easier. We're ultimately not asking you to just memorize anything just because we told it to you, right? Science really isn't supposed to be that way. All these things are supposed to actually make sense and come from a place that human beings figured out, and we're human beings, so we should be able to figure them out. But that can also be hard because we're not accepting anything just based on memorization. And all of us have gotten this far in life. We're used to sort of getting through school and getting through things like when in doubt, like memorize, or when in doubt, look things up. Now, when in doubt, look things up is a great instinct that I never want to discourage. When you don't understand something, you should look things up. But this is a long way of saying, I want to say to people, there's an equation for period that we are trying to build here, a full equation. We don't have a full equation yet. We have a direct proportionality. We know that T is equal to some constant times the square root of M. We know that because we figured it out experimentally. We don't know what that constant is yet. In order to believe that we know what that constant is, we got to figure it out. We as a class have not figured out the constant yet. So we as a class do not have an equation to plug in for a period quite yet. Of course, there is one, and it's look upable on the web. So a number of you have looked it up on the web and have been using it to get things and stuff. I'm not trying to discourage that. Of course, you should look things up on the web, and you should, like, it's knowledge, it's knowledge. I just want to be clear to all of you that it's not unfair for you to look up equations on the web. And it's not even cheating. It's not. It's knowledge. It's out there. What would be unfair and what would be cheating would be if I were to ask you questions that you could only answer from equations that you had to look up on the web and then I never taught you. That would be unfair on my part. Okay. And I wouldn't be doing what we're trying to do here in physics, which is build everything up from the. So I just want to tell you all, if you ever find equations from the web that seem to help you, oh yeah, no, like Quark bless America. Like have at it, but be clear in your mind that that's what you're doing. Like, I want you to know, if I ask you a question, looking up the equation on the web should not be the only way to do it. It wouldn't be fair for me to do that. There should be a way to answer these questions with the knowledge that we have so far. So just keep it straight in your mind. Some of you have an equation that you're tracking that you got from the web. I'm not saying it's wrong, and I'm not saying you should like throw it away. I'm just saying be clear that that's like maybe where we're heading, or it's a goal, or ask yourself, do you understand it or not? Or like when we get, like, make sure that maybe you really understand it once we get there. But just know that I can't assume that you have that equation that you got from the web if we haven't figured it out yet. Anyway, all right. So, but no, I'm not criticizing anybody. I'm just like, just keep it straight. All right. So right now, what we have in this class is we have that T equals some constant times M. Hopefully, we're now starting to get curious about maybe what that constant is, but we don't know what it is yet. Okay, so the period for this problem is now approximately 1.2 seconds. But now I'm also going to tell you a physics trick here, a physics technique, the way physicists think. The number of 1.26 seconds was 2 times 0.628, right? That's where I got it from. That 0.628 was not a coincidence in the first place. Like, it would be totally undercutting our own purposes if we didn't recognize that 0.628 is like 2 pi with the decimal place moved over, right? It's approximately 0.2 pi seconds. That's not, we should, since we're about to convert to pi and radians and all that, we should take advantage of that fact. We should try to make our life as easy as possible. I'm not saying you have to, but it would be the physics thing to do. So I'm saying the old period was like 0.2 pi seconds. It was like pi over 5 seconds. Therefore, my new period here is like double that. It's 2 pi over 5 seconds. You don't have to do this. I'm just saying I think it's going to make it easier. I'm expressing my new period. Also, it helps me get used to pi. Pi is just a number. It's approximately 3. It's a little bit more than 3. So the period here is approximately 2 pi over 5 seconds. That's the period. But the question is asking what's, the board, okay. The question is asking, what's the angular frequency? Now here too, you can either accept a memorizer that we sort of established a couple of weeks ago if you want, or you could think through the logic of this. Ideally, you'll be facile with both. I'm saying so we're asking angular frequency. We're asking number of radians per second here. Well, standard frequency measured in cycles per second, standard frequency is the reciprocal of period, right? Like we said that like an hour ago. Cycles per second is the inverse of seconds per cycle. So whatever we have for period, if we flip that, we'll have standard frequency. What's angular frequency? Angular frequency, first of all, from here on in, we're going to designate with the lowercase Greek letter omega. I don't remember if I said this last week or not, but I'll say it until I don't need to say it anymore. From now on, angular frequency is designated with the letter that looks like a W, but is actually a lowercase Greek letter omega. It stands for angular frequency. It is the letter that we're using from now on for what you originally in the lab called lowercase a. We originally called it lowercase a just because we didn't want to intimidate people with Greek letters and because that's what we know some of the software spits out and stuff like that. But whatever you were calling a in the lab, the standard physics term is omega. Now, omega is angular frequency. It's a way of measuring frequency, but in radians rather than cycles. Just because it'll make the math easier to do, it'll make it easier for us to take cosines and sines and things like that. So omega, so the conversion factor or the concept is just that for every 1 cycle, there are 2 pi radians. There's 2 pi radians constitutes a full circle or a full cycle. So if I say something is doing 3 cycles per second, each one of those cycles is 2 pi radians, I would just multiply the cycles by second by the radians per cycle in order to get radians per second. If something is oscillating at 3 cycles per second, then I can say it has an angular frequency of 6 pi radians per second. Literally, I'm just multiplying by 2 pi. Notice, if you multiply by 2 pi radians per cycle, if you multiply cycles per second by 2 pi radians per cycle, then the cycles cancel out and you have a number of radians per second. This is consistent with what you found in the lab. You found in the lab that omega is 2 pi over the period. Sure, because 2 pi times the frequency means the same thing as 2 pi over the period, because frequency is 1 over the period. So whichever way you do it, I'm saying if we're trying to get the angular frequency of this oscillator, however you do it, if the period is 2 pi over 5 seconds per cycle, then the frequency is, flip that, is 5 over 2 pi cycles per second, right? And then multiply the whole thing by 2 pi radians per cycle, and you get, and the 2 pi's cancel. And that's why I expressed in terms of pi, because I was hoping something like that would happen to make my numbers clean. The 2 pi's cancel, and I get omega approximately. Sorry, this is all approximate because, sorry, this is all approximate because I rounded. Okay. So I get in the end that omega is approximately 5 radians per second. Those of you, and there were people in the chat, those of you who didn't do this pi trick, and would I expect you to think of this pi trick on your own? Maybe, maybe not. But would I encourage you, it doesn't matter if you would think of it on your own. Now that you see it, I would encourage you to think of to recognize pi when you see it and do your numbers in terms of pi when relevant. But of course, most of you didn't do that, and that's fine. So in the chat, if you were just plugging the numbers straight in and you got something in the chat, like if you got something more exact on your calculator, like 0.49 radians per second, oh, I'm totally with you. Like, you're right. Like, we're doing the same thing. I'm just doing it a different way. So if you got approximately 5, if you got like 0.49, it's totally right. And if this were an exam, I would call it totally right. Okay, so that's the answer to that one. Stop me if not. So now the next, and maybe I made a mistake here because I did see some of your answers in the chat. Maybe well, the first one, I think most people are in agreement. After that, let's think carefully because maybe I made a mistake. But you could start plugging these numbers straight into your calculator, and people were. But if you're plugging these numbers into a calculator, okay, one thing, and I did hear about this from Professor Talley, and and from some of you, if you're going to use a calculator, which of course you can and should, your calculator has to be in radian mode. This is all assuming radians. This is all assuming that there's 2 pi radians to a circle, not degrees. So, I mean, how you do that on your calculator depends. I mean, the more expensive the calculator, the harder it is to switch modes. But usually there's a button that literally says mode, and you press that, and then you wait. And okay, sorry. Okay, fair. No problem. Oh, okay. I appreciate your honesty. Wait. Okay. Hold on, I'm just responding to the chat. Okay. So if you're in a calculator, what just happened? Okay. If you're in a calculator, be in radian mode. If you want help with that, like, I'm happy to help you, but it might be hard unless I physically see the calculator. But I'll also say this. If you're ever not sure what mode you're in, I suggest that you type in something like 30 and hit sine. I mean, I think that's one of the more, because if you're in degrees, the sine of 30 degrees is 1/2. And I think a lot of you know that, or maybe should know that, or want to remind yourselves of that. The sine of 30 degrees is 1/2. Of 30 degrees is 1/2. So if you type in 30 and you get 1/2, you're in degree mode. But if you type in 30 and you get some wacko number that you don't recognize, that's good. That means you're in radian mode, for what it's worth. But now I'll tell you that this first one of D, I didn't use my calculator. I didn't use my calculator for the first two. And maybe I made a mistake on the second one. You tell me. I want you to think with me here. The very first one, I didn't use my calculator because I looked at the problem and it said, the very first one said at t equals, I believe, 1256 seconds, right? I believe it asked, where is the mass at t equals 1256 seconds? Now, if I recall, like the period was 1.256 seconds, right? So, and this is not a coincidence again, like you want to assume that these questions are being asked for a reason often. And stop me if I'm wrong about this, but I believe the period was 1256 seconds. I mean, 1.256 seconds, but it's asking where is the mass at 1,256 seconds. Sorry, that is an integer multiple of the period. An integer multiple, meaning like I just moved the decimal point over 3 times, meaning what is that? That's 1,000 cycles, but not just like roughly 1,000 cycles, like exactly 1,000 full cycles. Like that number is not a coincidence, or it looks very familiar to me. So it seems to me that that amount of time, 1,256 seconds, is the amount of time for this thing to go there and back fully, exactly 1,000 times. Now, do I really care that it's 1,000? No, what I really care about is it's some whole number. I feel like because of that the number 1,256 seconds, that this thing should be back where it started once the time has elapsed. And where it started was the initial position of 0.4 meters. That, and I'm being serious about it. I'm not being sarcastic. That is the logic that we're sort of, if you looked at those numbers, and this was true in phase 1, the first 3 numbers it's giving you were non-coincidentally, they were like very much based on the period number. So it's asking you about special moments in the oscillation. I feel like the first answer is an amplitude moment. But then so stop me if you don't agree. Because then on the second one, a lot of people seem to disagree with me. So something might be funny. But on the second one, I believe it asked, let me check. I believe what did it ask? The time amount that it gave for the second one, the time amount that it gave for the second one. Oh, it's 3.1. Now, I don't know why exactly it skipped, but oh yeah, I do. All right. The second one, it said at 314 seconds. In other words, 100 times pi. Yeah. So what is that? That's a quarter. Like that's how can I put this? That's a quarter of the cycle times 100. What am I trying to say? Yeah, I don't know how to put it better, but I mean that if a full cycle is 1.256 seconds, then a half cycle is 0.628 seconds, right? And a quarter cycle is 0.314 seconds. So this is 1,000 quarter cycles. Now, I don't really care that it's like literally 1,000. I care that it's a whole number, an integer multiple of quarter cycles. So in a quarter cycle, so in a full cycle, you go all the way there and you come all the way back. In a half cycle, you go all the way there. In a quarter cycle, you go to the equilibrium position. So I feel like the answer to number 2 should be y equals 0. I know some of you did not get that, but I think that maybe either your calculator was not in radian mode or something. If you got super close to 0, then we're just talking about rounding. It's no big deal. But I think that's the answer. And I also know we only have about 15 minutes more in class. So I'm going to assume, I mean, if there's any question or disagreement, please put in the chat, but I think that's the answer number 2. And I think would be great if we actually finish this. I think you would like that. So I'm going to go on. So now you might say, what about the, you keep getting 4. Am I thinking about something wrong? You keep getting 4 and you're in radian mode, right? Okay. And someone else, and you're not the only one. So let me think about that. All right, you know what? Let's put a flag on. I will not forget. I have a feeling because you're not the only one, because 2 of you are saying that, and because that number 4 is, there's something reason. Wait, you're getting 4.
Can I tell you? I did just the cosine 2 pi over 1.256 times 314, and I got 1. So it's 1 times 4, and I guess that's how I keep getting 4.
Wait, okay. That's very cool. Although, wait, one thing, when you say times 4, don't we mean 0.4? Not to be weird, but...
Oh, is it 0.4? Did I mess up? Because that could have been me. I don't know.
No, that's not a big deal. I mean, wait, hold on. I'm clarifying for myself. I think it's 0.4, and I'm just clarifying that for myself just to make sure I'm not crazy. But that's not even the issue. I mean, I'm not saying you messed up. That's not... Like, wait,
I'll redo it with 0.4 and I'll let you know.
Oh, you'll still know. I mean, then you'll just get point. I mean, you're saying that you're not getting 0. I totally believe you. And if you redo it with 0.4, you're gonna, like, you got 1 and you multiply by 4, so you got 4. So if you change it to 0.4, you're gonna get 1 and multiply by 0.4 and get 0.4. Okay, wait. And I'm but no, I'm with you. And you're not the only one. I think 3 other people are doing the same. Hold on. Yeah, 3 other people are getting the same thing you do. So I think you must be right. Hold on a second. You're still in before. Yeah, 3. There are 3 of you, and you're all doing it. No, you're definitely with me. So wait. So what am I? All right. So I'm doing something wrong on that one because it's just too logical. Wait. And 0.4 means it is an integer. I do see what's happening. I totally see. No, you're totally right. All 3 of you are totally right. I'm being too fast and loose. You're totally right. You are right. And I see it's not even worth it. My explanation will come. I'm going to do the next 2 so we get answers to all this. And the next 2, I'm going to do your way. So hold on. Hold on a second. You are right. You are right. We are saying 0.4 though, right? Yeah. The fast, that's very good. And I'm glad you all are holding your ground. And I'm glad that you're paying so much attention. The first 2 I did by like a trick or by logic. And you guys did the equation. The next 2, I'm going to do the equation. So we're all going to be on the same page. The reason, and of course, the logic should jive up with the equation. Otherwise, one of us is wrong. So you were all right to protest. The quick thing I'll say, and then this will either make sense or not, but you'll see when I do the equation next 2, you are right and I am wrong. And the reason is because the logic I keep saying is that if it's an integer multiple of the period, then it's going all the way there and coming back and landing on its original spot. Well, I'm an idiot because 314 still is an integer multiple of the original period was 1.256. So I'll do it on calculator right now to show the point. This is to show why you are right. This is to show why you are right, not why I'm right, but why you're right that the trick should still yield the same as the equation. The point is that, where to go? Yeah, I'm such an idiot. I said for number 2, I said, 314. Well, that's 100 quarter cycles. Excuse me. I said that's 1,000 quarter cycles. So it should land at a quarter of the way at equilibrium. Well, that's not wrong, but it's stupid. I said it's 1,000 quarter cycles. What is 1,000 quarter cycles? It's 250 full cycles. Like, I did the quarter too early in the math. Like, I'm just being dumb. Like, it is 1,000 quarter cycles, but because it's 1,000 quarter cycles and 1,000 is evenly divisible by 4, it is in fact 200. In other words, 314 is evenly divisible. 1.256 evenly divides into 314. And I'm just an idiot for not having realized that. So you are totally right. You guys, all three of you, four of you, five of you in the chat who got 0.4 by plugging the equation, you're right to plug in the equation. And I just want you to also see the logic is still true, that as long as we're doing even multiples of cycles, we should end up where we started. Well, we did do an even multiple of cycles. I'm just dumb because I was calling it an even multiple of a quarter cycle. But I don't know if that, and if you don't know what I'm saying, don't worry about it. Just trust those people are right. The answer to number 2 is 0.4. Now I'm going to go on and actually do the equation like, oh, you're very kind. Okay, you're very kind. Thank you. No, I'm never allowed another mistake again. If I make another mistake again, whatever. All my Pokemon fade. Okay. No, thank you. I appreciate it. So, all right, now I'm going to quickly, we've got 10 minutes left. I'm going to do the equation for the next 2, just like you did them. And we should all get the same answers. And then we'll be actually. Wait, let me just look at the rest of, hold on. We have 10 minutes. I just want to look at I know there's other questions on the sheet. I want to see if yeah. The one thing I'm going to tell you right now we're not going to get to today is the diagrams, which may be what you really want to see. I respect that. I'm not going to be drawing diagrams today. That will take a little longer, but I will give you the answers to the rest of the sheet. Yes, I will give you the answers to the rest of the sheet like right now. In fact, I'm just going to write it out. I won't talk for the next 10 minutes. I'll just write it out. So. Okay, so those are the answers to those 2. I'm just plugging the equation like you guys did. I think what I'm trying to argue is that we plug into equation as a last resort, like if it's not a special angle or special moment, but those 157 to 57 are not special. Well, actually, well, whatever. So I plugged into those, and those are the answers I got there. Hopefully, that's what you got too. I saw in the chat, but let me. Okay. But now I'm going to go on. So if you got the first 2 right, we're just plugging into the same equation, and that's it. I guess just notice the whole point of the cosine equation is that when you plug into cosine, well, cosine. The whole point of the cosine equation is that it returns values that fluctuate, oscillate between 1 and -1, 1 and -1. So then to convert those 1 and -1, the pure numbers, to convert those numbers into actual distances measured in meters, we multiply the whole result by y naught. Right? Y naught is the original and maximum displacement measured in meters. So it's just taking the whole cosine graph that goes from 1 to -1 to 1 to -1 and just stretching it and placing it in metric space, right? And the omega term inside the cosine is just determining how quickly the cosine graph is cycling. Omega is measured in radians per second. So it's basically saying how many cycles does it do for every unit of time? Okay, so that's it. That's what that thing is doing. Now, just to quickly I'm just going to write out the answers to the next questions on the last sheet. I don't know if you did them or not, but I'm going to write out the answers right now so you can check, and we'll call it a day for right now. Or, you know, and you can look, well, anyway. Well, I mean, it's all based on the unit circle, but not in the intense, like, horrific way that like Remy and other people might be remembering. When I say unit circle, I mean, I'm picturing a circle with radius 1, and cosine and sine are just the coordinates, x and y coordinates of a arrow of length 1 that's pointing to the circle. So if I just look at that picture, I think the cosine of 0 is 1. I think the cosine of pi over 2, which radians, which is half. So cosine of pi over 2, 2 pi radians means around the whole circle. Pi radians means half the circle. Pi over 2 means a quarter of the circle, a 90-degree angle, right? So, I mean, what's the cosine if I'm pointing straight up? I think it's 0. What's the cosine? So I'm just writing these out. Like, I'm not memorizing these. I'm just realizing that, you know, this must be 1, 0, just like you guys told me last time. And these are pure numbers. Sine and cosine just return pure numbers. They're never greater than 1. They're never less than -1. So those are my answers to those. 706. I want to turn the page, but I'll turn the page. We have 4 minutes. I'm going to turn the page and write the rest of the answers. And you tell me if you want me to turn the page back or what. But we're done and we'll talk about all this next time or whatever. But this one does require thought. I will have to explain this next time, but I'm just giving you the answers so that we have some closure for today. Yeah, I believe that's, yeah, I'll pick up on this next time, but I believe those are the answers. So let me put it this way. If you've copied down the answers, and you're fine for the moment, have a nice night. If you want me to turn back the page or answer any questions, I'm here until the last person goes. But I'm good if you're good. But you've been very patient. I think we got some stuff done. We've gotten through the whole sheet. I don't know what else to say. No, and I'm going to turn off the recording. But yeah, I'm good if you guys are good.